Welcome, fellow chemists, to the latest video in the instrumental analysis series where we will be introduced to infrared spectroscopy. Like with mass spec, I'm going to leave out any math and physics not explicitly required to analyze the spectra we get from the instrument itself. But why can infrared radiation be used in the first place? Some molecules like nitrogen and oxygen don't absorb any infrared, but others like water do. Absorption doesn't destroy the molecule, but instead the molecule wiggles in response. What I called wiggles are more commonly referred to as stretches and bends. During them, bond lengths and orientations change. For this video, we are going to ignore the minute details, but in order for any of them to happen, the molecule must absorb infrared. And if infrared is absorbed, it does not reach the detector, which is what the spectrum reveals. The y-axis records the amount of radiation that hits the detector as a percent. If a molecule absorbs all the radiation, then the transmittance is 0. The more that passes through, the higher the transmittance goes. Sometimes the top of the y-axis is not 100, and I'll show you that soon. On the x-axis, we find the frequency of the radiation. The unit is wave numbers, but don't worry if that is unfamiliar. Higher frequencies are recorded to the left, and lower frequencies recorded to the right. The spectrum does not just show one data point, but one for each frequency, all 3,600 of them. And when all of that data is plotted, this is what it can look like. In order to generate the graph myself, I needed the actual data, and links to the sources can be found in the script. The most obvious question to ask is, how on earth do we read this? Since the highest transmittance percentage is about 70, I can make the spectrum a bit clearer by making 70 the height of the y-axis. With the aesthetics improved, let's get to the analysis. Thankfully, we get to stand on the shoulders of chemical, physical, and mathematical giants because it is well known now what wave numbers correspond to which bond type. I mean, if you'd like to, feel free to calculate the wave numbers for whatever bond you'd like. Go ahead, here's all you need. When discussing the spectrum, it's often split into two regions. First, we have the area from about 1400 to the right. For two nearly identical molecules, this region will reveal their uniqueness, which is why this is known as the fingerprint region. The left side is the functional group region, and this is where we will focus our attention today. The first functional group, often the easiest of all to identify, is the alcohol. If it's present, we find a peak near this region on the left. The width of this and all others is an approximation. With the addition of the next functional group, we see the difficulty with interpreting IR spectra. The nitrogen-hydrogen bond shows us smack in the middle of the alcohol region. I'll separate them for clarity and do that with the rest. Now this one represented by the yellow region is not the alcohol again, but is the OH bond and a carboxylic acid. As the remaining bond types display, we get a nice picture that we can use as a reference. Over time, identifying the presence or absence of any of these will not require any more than a quick glance. But we can convert this to an easier to read chart with a column titled intensity. Not all peaks are as intense as others, and the terms, though possibly vague, allow us to distinguish between functional groups that show up in the same region of the spectrum. It might be easier to see these terms used in practice, so let's try it. And for the first of two practice spectra, we'll start with the one that was on the screen earlier. It is a rather simple molecule, and we will use the previous charts to help identify what structural components it may contain. Pause the video and give it a go yourself. We will start with alcohol, which should have a strong, broad peak in this region. Strong means it reaches from the top far down, and broad means, well, broad or wide if you prefer. Clearly there is something in this region, so I'm going to move OH to the side since it's a likely component of this substance. NH peaks show up in the same region but are not as strong as the alcohol. This peak is quite strong, so we can eliminate NH as an option. Next up is the carbon-hydrogen bond range, where we find peaks in the middle. For an organic molecule, this is unsurprising. However, after those comes the carboxylic acid, and those peaks fit in that range too. The description of strong and very broad is extremely helpful now. These peaks are narrow, covering only 200 wave numbers, which means a carboxylic acid is unlikely. The next peak doesn't show up until below 1500, so we get to rule out a bunch of structures from consideration. As for benzene, this peak seems to indicate its presence, but don't get fooled as we just eliminated carbon-carbon double bonds, and benzene rings have another peak around 1600, which is missing. That leaves carbon-oxygen and carbon-nitrogen, which fall in the same region, and there are peaks present. Given the likely presence of an alcohol, a carbon-oxygen bond is more likely of the two. Our interpretation of the spectrum leaves us with an alcohol on an alkane because there are no double or triple bonds. On this spectrum alone, this is about as good as we can hope. If we have more information like the mass spec or NMR, then we could probably identify it, which we will do in the future. But for now, what functional groups are present in the molecule that produce this spectrum? The broad peak on the left just barely passes through the alcohol range, so for now it might be present. There is something in the NH range, but doesn't appear as good a fit as the OH, so I'm going to ignore it. Next up is carbon-hydrogen, and that fits. The broad peak on the left is an absolute match for a carboxylic acid, so it no longer makes sense to keep the alcohol. Triple bonds are definitely missing. The strong peak around 1700 certainly indicates the carbonyl, which even better is part of the carboxylic acid. This means we can safely ignore the other double bonds. The benzene ring once again is a partial match, as like before, the peak around 1600 is missing completely. That brings us to the carbon-oxygen bond, which has a peak within the range, and we know that it is part of the carboxylic acid structure. Finally, carbon-nitrogen bonds are not as good a match as carbon-oxygen, plus without any evidence for NH bonds, it's safe to rule it out. So the best we can do is say the spectrum was produced by an acid with an alkane chain. Although that's not entirely accurate. We did determine there are carbon-hydrogen bonds, but on an organic molecule that's not really a surprise. What we will do in the next video is take a look at the variety of carbon-hydrogen bonds, where those peaks fall on the spectrum, and how we can use them to help us narrow down the potential identities even more. But until then, thank you very much for watching. Please feel free to leave any questions or requests in the comments below.